Thank you, Professor Segal. Finally, we will hear a pre-recorded talk from Dr. Sophia Rein at Harvard. She couldn't travel for some personal reasons. Can we pull up the video, please?
Good afternoon to everyone in the audience. It is my pleasure to provide an overview of our project titled Causal AI for the Generation of Real-World Evidence from Healthcare Data. And first of all, I want to say that I'm honored to have been awarded a health science grant from ADIA Lab, and I want to thank the organizers for giving me the opportunity to present our ideas here at the Symposium. And so I want to start by providing an overview of the background and motivation of our project, which is that health systems around the world generate vast amounts of data every day. For example, in the form of electronic health records, insurance claims data, and registry data. And in a learning health system, these data provide a rich source of information that can be used to generate evidence about the effectiveness and safety of medical interventions. And so while the theory and methods exist to estimate the causal effect of medical interventions from such observational data sources, the validated analytic tools to implement these methods at scale currently lag behind. And so as a result of this lack of tools, health systems cannot fully learn from their own data to improve decision-making within the system itself. And so in terms of the theory and methods that have been developed for causal inference, the G-formula or do calculus provides a general framework for causal inference from complex longitudinal data. And one commonly used representation of the G-formula is the so-called non-iterative conditional expectation, or NICE G-formula, and that algorithm computes the expected outcome, for example, the risk of a disease under different interventions, by integrating or summing over the joint distribution of the covariates in the data. And so these covariates could be any data that we believe influences which medical interventions someone is receiving and whether they will develop an outcome of interest, such as a disease or medical condition. And of course, there can be many such covariates in real-world data that we want to account for. So this could include different lab measurements, different comorbidities over time that influence each other in a complex way. And so correctly modeling this joint distribution of the covariates is very important to this method. And the method has been widely used, but existing tools typically use standard parametric models to model these complex relationships in the data. But these parametric models are prone to misspecification, especially when the covariates exhibit the complex long-range dependencies that are common in real-world data. And causal AI tools that are capable of capturing complex relationships in real-world data do not yet exist. And so the key aims of our project is to fill this gap by first developing a software tool for causal AI that can be used by health systems and researchers to generate evidence at scale. And then to demonstrate the application of this software with a use case on cardiometabolic disease. And so the idea for the software really is to develop a deep learning-based NICE G-formula estimator that uses deep learning models to model the joint distribution of covariates and the outcome. And specific models that we want to use here are so-called long short-term memory models, or LSTMs for short. These are models that were specifically developed for longitudinal data, and compared to parametric models, they can better model complex long-range dependencies between variables. And so with this approach, we might be getting more accurate estimates of the causal effect of treatments in healthcare data due to this less model misspecification. And so another key feature of the software will also be that it incorporates techniques from machine learning, specifically sample splitting and cross-fitting, to enable valid statistical inference and uncertainty quantification for the estimates. And so I now just want to give you a high-level overview of the steps of the AI-based NICE algorithm with uncertainty quantification, just to give you an idea of how this would work internally in the software. So the first step is to split the data into two halves. Then the first half of the data is used to train the LSTM models and to select the best configuration or the best set of hyperparameters for the LSTMs. So there will be one LSTM for joint prediction of the covariates and one LSTM for the outcome. And the next step is to fit the models to the second half of the data and estimate the G-formula outcome risks under the sustained treatment strategies that are of interest to the investigator. Then we perform cross-fitting, which involves swapping the roles of the first and second half of the data and repeating the process. And at the end, the split estimates will be averaged and confidence intervals can be reported to assess uncertainty. So in terms of the features and the architecture of the software, we want it to be as flexible as possible. So users will be able to estimate the causal effect of arbitrarily complex sustained treatment strategies. And internally, the software will automatically configure and train the LSTM models after the users supply the treatment, the outcome, and confounder variables without requiring users to manually specify the models. The software will also support end of follow-up and survival outcomes, which are both common in medical research. And beyond that, we also want to incorporate parallel computing and other techniques into the software so that it's as efficient as possible and can really be used at scale on large data sets. And before we use the software in any real data, we will conduct a simulation study for validation and to evaluate performance of the method and the software. And so the other aim of our project is to apply the software to a use case on cardiometabolic disease once the software has been validated. And specifically, we want to estimate the effect of GLP-1s versus other antihyperglycemic drugs on cardiovascular events among adults with type 2 diabetes. And so this is a question of high clinical importance, but randomized clinical trials rarely follow patients long enough to capture these long-term outcomes. But on the other hand, longitudinal data from routinely collected healthcare data are well suited for this question. And so what we will do here is to use healthcare data to emulate a target trial, which is the hypothetical randomized trial that we would ideally like to conduct to answer this question. We will emulate this using our healthcare data and then estimate the intention to treat and per protocol effects in our data. So we plan to use both data from the US and from the UAE. The US data will be data from MarketScan, which is an administrative claims database and the largest US data set based on commercial health insurance claims. Then we propose to use data from Malafi, which is Abu Dhabi's centralized health information exchange, which provides access to the unified medical records of around 13 million patients. And so in each of the two databases, we will then emulate a target trial to estimate a causal effect of interest. And so in that target trial, we would include individuals age 30 or older with incident type 2 diabetes on metformin. The treatment strategies that we want to compare are to initiate GLP-1s versus other antihyperglycemic drugs. The outcome of interest is MACE-4, which includes myocardial infarction, ischemic stroke, heart failure hospitalization, or cardiovascular death. And individuals would be followed from treatment assignment to the earliest of the outcome, loss to follow-up, or administrative end of follow-up. And key confounders that we would control for in the data set will be defined with clinical experts from both settings, in collaboration with clinical experts, but they will include variables such as age, sex, comorbidities, medication history, and healthcare utilization. So to really summarize the innovation and potential impact of our project, we will be developing the first open source software for causal AI based on the G-formula. And our idea is for this to be a tool to transform complex clinical data into real-world evidence that is accessible to everyone. And so the first application of the software will be on a use case based on a clinically important question that can inform treatment decisions both in the US and the UAE. And we also aim to establish collaboration between US and UAE researchers and stakeholders from different fields and areas that can enable knowledge exchange and strengthen analytic capacity. Thank you very much for your attention, and please do reach out for questions or to connect. My contact information can be found by scanning the QR code on this slide.
I'd like to thank all three of the principal investigators again. The principal investigators will also join ADIA Lab as the fellows for the next 2 years, the duration of the grant. So we'd like to welcome you to the ADIA Lab family.